Professor, can you hear me?
Yeah, can you hear me okay?
Professor, can you hear me now?
Yeah, can you hear me?
Yes.
Perfect. All right. Well, hello, good morning, everybody. I hope you're all doing well. As you know, this week we are just covering one sort of elongated topic. So we'll be continuing what we were working on Tuesday. And as a reminder, there's only one mini quiz this week, and that's due on Sunday. So if you were looking yesterday and there wasn't one there, it's because we only have one mini quiz this week. So I'm going to switch on over to the dot cam here. All right. So just as a reminder, this week we are talking about the chain rule, and the chain rule is the way that we approach derivatives when we're dealing with composite functions. And so we've been looking at different types of chain rule forms. And last time we looked at the power rule and we started the exponential rule. So we're going to pick up with that, working on some exponential functions, and then we'll just keep moving through the different types of rules until we finish them all. So we were working on exponentials, and so I'd like us to start with these two particular problems to just sort of remind us about how these exponential rules work. So for example 3, we're looking to find the derivative of e raised to the x to the fourth minus ln x plus 1. So as a reminder, you can do a z substitution where you're going to use z as the power of e. And then you could also sort of reason through using the rule we talked about for exponentials. But for example 3, you're just finding the derivative. And then for example 4, we're going to do an application where we have a demand curve and we are trying to figure out f prime of 6. So you'll see here that this is an exponential form. So we have to take the derivative before we plug in a 6. Okay, so we're just going to jump right in. We're going to start with that. I'm going to give you about 3 minutes to see if you can sort of remember what we were doing, bring it all back. Feel free to look back in your notes from Tuesday to remember how we were approaching these exponentials, and then we'll go through them together. So give those two problems a try. All right, take about 30 more seconds. All right, so let's review these. So again, the sort of key thing that we need to do here is recognize that we're looking at something in the exponential form. So we have e raised to something where we see the variables up in the power, and we see that it's more than just e to the x. So we know it's a chain rule, and we see it's exponential because the variable's in the power. So again, you may have reasoned through this and used sort of the other method of doing this, which is totally fine. I'm just going to do some of the z substitution just so we can review it. So again, your z is going to be whatever is up in the power, which here is e to the fourth minus ln x plus 1. And then we're able to rewrite our original function as e to the z. So again, the idea is to break this down into functions whose derivatives we can take based on that basics chart we had before. So the derivative of z with respect to x, if we go term by term here, we're going to get 4x cubed from the first term minus 1 over x from the ln term, and then the derivative of 1 is 0. For our e to the z, the derivative of y with respect to z, the derivative of e to the z is just e to the z. So now we want to multiply these two things together. And I will note that this has more than one term, so I'm going to use parentheses. So I have 4x cubed minus 1 over x times e to the z. But as we remember, we don't want a z in our final answer. So I have 4x cubed minus 1 over x times e. And now I have to substitute back in what z represented, which here is x to the fourth minus ln x plus 1. So if you did this with the other method, you should still have these two terms. And again, I just want to highlight how important it is to have these parentheses around the term, because it's these two things multiplied together, which means it's the whole thing of this times the whole thing of this. If the parentheses were not here, it would not be correct because the e would only be multiplying the 1 over x term. Okay. So that's that first one. The second one, we are applying an exponential function to a specific situation. So we have the demand curve for a product, which says, depending on how much you charge for a product, we'll tell you how much people are going to want to buy, is what a demand curve tells us. So here, the Q is the quantity and P is the price, and we want to find and interpret f prime of 6. So let's start by just finding the general derivative, and then we'll talk about what it means. So we start by finding f prime of p, not of 6 yet. We're going to find the general derivative first, and then we'll plug in the 6. I skipped a step here. So what we want to do is we want to look at our function, and I notice that we have a 4,500. So that is a constant multiple. So that is going to multiply my derivative. And now my function is e to the negative 0.15p. So I see it's exponential. I see that there's a number up in the power. We've already talked about how to deal with this algebraically, but we can also bring in the chain rule here. So I can say, okay, I'm going to get the same thing back, e to the negative 0.15p. And then I have to multiply this times the derivative of the power. So that's the other way we approach this. So the derivative of negative 0.15p is negative 0.15. So now I want to combine my two constants. So I'm going to multiply negative 0.15 times 4,500. So I believe that will give you negative 675 e to the negative 0.15p. So again, I just combined my two constants. And now I'm interested in what's happening when my price is $6, right? So I'm trying to figure out what is the demand when my price is set at $6. So here, if I plug in 6, I'm going to plug that in up in the power. Okay, I'm going to plug this all into my calculator to see what shakes out. And I get negative 274.43. So what does that tell me? So remember, when we talk about the units, we're going to do the units of the dependent variable over the independent variable. And the dependent variable here is just quantity. So we can call that item, right? Item sold. So we have items sold per dollar. So what does that mean? That means that for every additional dollar we charge, right, to go from $6 to $7, the number of items sold is going to be decreasing by $274.43 per dollar, extra dollar charged. So we can see that our demand is going down as we raise the price. So that's what that tells us. But again, we had to use the chain rule here in order to find our derivative. So those are the exponential function examples and rules, and then we obviously have the ones we did last time as well. So the next type of rule we're going to look at is the chain rule for the natural log. So that's the next type. So we've looked at the power rule, we've looked at exponentials, and now we're looking at the natural logarithm. So again, here's an example, right, where we have something complicated inside the natural log. And again, we want to simplify it by substituting in a z and figuring out what our z is going to look like. So when we think about a composite function, the inside function here would be this x to the 5th minus 3x squared plus 1. So we start again with our z substitution, so we can see what's going on in the background. And when we pick our z for natural logs, your z is going to be whatever's inside the natural log argument. So we have x to the 5th minus 3x squared plus 1. And then we want to rewrite the original function with the z in it. So we substitute in z into the argument, because that's what we're subbing in for. Now we need to take each of our respective derivatives. So for the first one, we're going to get 5x to the 4th minus 6x. And then the derivative of 1 is 0. And then dy dz, the derivative of the natural log of z is 1 over z. Okay, so again, this is the same process we were doing on the other types. The difference here is just that we're looking at a natural log type. So when we take the derivative of the natural log, we have this 1 over z. So now we want to multiply these together. So I'm going to use parentheses. So 5x to the 4th minus 6x times 1 over z. Again, I don't want a z in my final answer. So there's two things I'm going to do in this step. First, I remember that everything is over a 1 power, so I can multiply this into the numerator. So in the numerator, I have 5x to the 4th minus 6x. And now in the denominator, I have 1 times z, but I'm also going to substitute back in for z in this step, as usual. So I have x to the 5th minus 3x squared plus 1. So that's what my derivative looks like. So whenever you're doing a chain rule on a natural log, you're going to end up with something over something, right? So I'm going to have you try one using the z substitution. We have the natural log of cosine x plus e to the x. I want you to take 2 minutes and do out the z substitution for this particular problem. Try it out, and then we'll try it out together. All right, take about 30 more seconds. All right. So again, when you have something with a natural log as the outermost function, we see that we have to use a chain rule because there isn't just an x here, right? If it was just ln x, we would use that the derivative was 1 over x, but obviously we have something more complicated here. So we do our z substitution by letting z equal whatever is inside, which allows us to simplify the original function into the natural log of just one variable, the natural log of z. So now we take our derivatives. Oops, so dz dx. Again, the dependent variable is z, the independent variable is x, so this is dz dx. The derivative of cosine is negative sine, plus the derivative of e to the x is e to the x. And then for our second derivative, we have dy dz. The derivative of the natural log of z is 1 over z. So now we're going to multiply these two things together. And again, parentheses, because there's more than one term. Negative sine x plus e to the x times 1 over z. And again, I don't want a z in my final answer. And I'm also going to multiply this into the numerator. So I have negative sine x plus e to the x divided by, and I have to substitute back in for z. So cosine x plus e to the x, okay? So that's what the z substitution looks like. Again, the process is the same as the other types. It's just what you end up with derivatives changes. So the other way that we can think about this is if we know that z and x are differentiable functions, then when you have to take the derivative of something that's complicated, the natural log of something complicated, you can think of it as 1 over that thing that's complicated times the derivative of the inside. So what does that look like? So here, if we go back to the one we were just looking at, which is the natural log of cosine x plus e to the x. Okay, so what this shortcut says is, hey, the derivative of the natural log of x is 1 over x. So when you start your derivative, instead of doing 1 over x, do 1 over whatever's inside there. Right, so we have 1 over whatever this stuff was. But then we have to remember to multiply that by the derivative of the inside. So the derivative of this stuff. So the derivative of cosine is negative sine. The derivative of e to the x is e to the x. And just like before, we can multiply that into the numerator. And we get negative sine x plus e to the x over cosine x plus e to the x. So again, this is telling us that whatever is in the argument is going to go in the denominator of our derivative. And then the derivative of whatever is in the argument ends up in the numerator. So we can do 1 over the stuff times the derivative of that stuff. And I want to point out that in the derivative, there is no more natural log, right? That disappeared from the work that we were doing. So let's try a couple of examples with natural logs here. Okay, so we have 3 examples. The first 2 are finding derivatives. So you can either use the z substitution, or if you feel better about thinking through the conceptual ideas and using the second method, that's fine as well. But for these first 2, you're just finding the derivative. For example, 4, we're going to take it a step further. As you can probably anticipate, we're going to find the equation of the tangent line. So again, same as all the other equations of the tangent lines, we need a point, we need a slope. The derivative comes in to help us find the slope and put it together to find a line. So I'm going to give you about 5 minutes to try out these 3 problems, see what you can figure out, and then we'll go through them together. All right, take about 30 more seconds. All right, so let's go through these. Again, it doesn't matter if you use a z substitution or if you use your conceptual understanding of the derivative, you should get the same derivative in either case. So I'm just going to alternate. So I'm going to start with the sort of conceptual understanding we just talked about. So if we try to reason through and remember all the pieces here, we know that we can do 1 over whatever is inside our natural log function. So here we have 4x to the 8th minus 2x squared. But we have to remember that it's not enough to just do 1 over that function. We have to multiply our derivative by the derivative of the inside. So the derivative of this 4x to the 8th minus 2x squared. So the derivative of 4x to the 8th, the 8th's going to come down. We're going to get 32x to the 7th minus, and then here we get 4x to the 1. Again, you don't have to write the 1, you can write the 1. And then finally, the convention here is to move this term into the numerator, multiply it by 1, and we get 32x to the 7th minus 4x divided by 4x to the 8th minus 2x squared. Okay, so your derivative should look something like that. It should have those two terms, with the bottom term being the 4x to the 8th minus 2x squared, and the top term being the derivative of that. Okay. Next, find the derivative of y equals the natural log of 3x. Now, this one might seem simpler than the last one we did, but more people tend to get this type of problem wrong because for whatever reason, they don't realize that that 3 turns this into a chain rule, right? So typically when students get this wrong, they say the derivative is 1 over 3x, and that's all they write. But let's see what actually happens here. So if we do our z substitution, our z is whatever's in the argument, which is 3x. We need to take the derivative of that. So dz dx, the derivative of 3x is 3. Then we rewrote our y as the natural log of z because of our substitution. So dy dz is 1 over z. So then we need to multiply these two things together. So we have 3 times 1 over z. The 3 goes into the numerator, and then our z we substitute back in. So we have 3 over 3x. The 3's can cancel, and we actually have 1 over x. So again, the common mistake is that students try to say that the derivative is just 1 over 3x. It is not, right? Because you're missing the derivative of 3x, and that 3 that's here changes your derivative function. So make sure that if you see the natural log of a constant times x, that you do a chain rule and address the fact that that constant is in there, okay? So now let's look at number 4. We want to find the equation of the tangent line. And so we know whenever we're doing a tangent line problem, we need a point and we need a slope. So let's start by finding our point. Doesn't matter which one you find first. To find our y value, we need to plug the x value into the function. So we plug in a 1, we get the natural log of 1 squared, which is the natural log of 1. And if you check that, the natural log of 1 happens to be 0. So we get y equals 0, and the point we're working with is 1, 0. Now, we also need to find the slope by considering the derivative, okay? So we had the natural log of x squared. So using the chain rule, I can say, well, that's going to be 1 over x squared, so 1 over whatever's inside, times the derivative of the inside. The derivative of x squared is 2x. So I'm going to simplify this by bringing the 2x into the numerator. So I have 2x over x squared. So if you're more comfortable plugging in like that, that's fine. You can also simplify this by canceling an x on the top with an x on the bottom, right? Which will just leave you with a 2 over x. Either one of these forms will give you the same answer when you plug a value in, okay? So now we're going to plug in our x value, which we said was 1, to get the slope. So we have 2 divided by 1, which means the slope of our tangent line is 2. So now we have to put everything together. We have our slope, we have our point. We're looking at y equals mx plus b here. So y equals 2x plus b. The 2 came from the derivative. Now we're going to use our point to be able to solve for b. So when x is 1, y is 0. So to solve for b, we need to subtract 2 from both sides, and we get b equals -2. So finally, we put all of this together, and we get y equals 2x minus 2. Okay? So again, whenever you're finding the equation of a tangent line, we need a point, we need a slope. Once we have those things, we put it all together. So the things that are changing are the type of function we have for f of x, but the process is always the same. Okay, so that is our natural log type. Again, when doing a chain rule with a natural log, you're going to recognize that you're doing a natural log because of the ln in front of the complicated function. So now we're going to move on to the next type, which is sine and cosine. Okay, so sine and cosine, just like all the other functions we've looked at, if you have something complicated in the argument, that's when we know we need to do a chain rule. And again, you know that it's a sine or a cosine chain rule because it starts with sine or cosine, right? So again, same sort of situation where we want to reduce this to a sine of a single variable. So we do that through a z substitution. So here for this particular one, our z is x cubed plus e to the x, which makes our y sine of z. By setting it up this way, we now have 2 derivatives that we can actually take. So dz dx, the derivative here, the derivative of x cubed, we get 3x squared plus e to the x. The derivative of sine is going to be cosine. So dy dz is cosine of z. And then again, we're going to multiply our 2 derivatives together. And because the first term has more than one term, I'm going to use parentheses. So 3x squared plus e to the x times cosine of z. But as always, I don't want a z in my final answer. So I substitute back in for z, which here was x cubed plus e to the x. So my derivative looks like this. And something I want to point out here that will be consistent throughout our work. Notice what was inside the sine is the same as what's inside the cosine. So what's inside the argument does not change. What changes is the actual outside function, so sine turned into cosine, and then we had to multiply it by something over here. But the inside of the argument stayed the same. Okay, so I want you to go ahead and try a z substitution. We have cosine of x to the 6th. See if you can use that same sort of map, figure out what your z is, figure out how to rewrite your y, find their derivatives, multiply them together, right? And I'll give you about 2 minutes, and then we will go over them together. All right, take about 30 more seconds. All right, so let's take a look at this. We start by identifying our z. Again, we're looking at whatever is inside the function. So here that is x to the 6th. Then we want to rewrite our function with our z in it. So here that's going to be cosine of z. And now we want to find each of these terms' respective derivatives. So again, the first one is dz dx, the derivative of z with respect to x. And that's going to give us 6x to the 5th. Then we want to find dy dz. The derivative of cosine is negative sine. So we have negative sine z. Now we want to multiply these together. So we have 6x to the 5th times negative sine z. We're going to simplify a little bit and substitute back in for z. So I'm going to pull the negative to the front. So negative 6x to the 5th times sine of, now I need to go back to what my z was. That's x to the 6th. So this is what the common answer would look like, and that's how we would present it. We always tend to pull negatives to the front, okay? Again, notice that we started with cosine of x to the 6th, and we ended with sine of x to the 6th. What's inside the argument did not change. So again, if we want to think about this more conceptually, we can certainly do that. Here we have this idea that if we're going to take the derivative of the sine of something complicated, we know that we're going to end up with the cosine of that same argument, but then we have to remember to multiply by the derivative of the inside. Similarly over here, if we have the cosine of something complicated, the derivative will be negative sine of that thing that was complicated, but we have to remember to multiply by the derivative of the inside. So if we were to apply this thinking to the last problem we did, we had cosine of x to the 6th. And so we use the fact that the derivative of cosine is negative sine. So we say, okay, negative sine x to the 6th, right? So we just did this part where we changed cosine and took the derivative to get negative sine. The x to the 6th stayed the same, but we have to remember to then multiply the derivative of this x to the 6th term. So we get 6x to the 5th. And again, typically constants come to the front. So we can rewrite this as negative 6x to the 5th sine of x to the 6th. So the same thing we got before, but we're just reasoning through it without doing all the sort of writing down of all the pieces. So two different ways to approach it, both equally valid. Okay, so let's look at some practice problems of sine and cosine. So we have three problems we're going to look at here. The first two, again, are just practicing the chain rule, practicing our derivatives. You can use either method. And then the last one is an application where we can see a function that's being modeled with sine, and we want to find a rate at which that function is changing, and therefore we would need to take the derivative. Now, in the last problem, it is a chain rule because instead of just having a t inside, there's a pi over 4. So we do have to do a chain rule here. So I'm going to give you about 5 minutes to try out these three problems. Again, the first two, you're just finding the derivative. And then the third one, we have this application. So try that out. And then in about 5 minutes, we'll go through them together. All right, take about 30 more seconds. All right, so let's take a look at this. So for the first one, we'll go ahead and reason through it. We'll see if we can think about all the pieces and not forget anything. So we start by thinking about the sine function. When you take the derivative of sine, you get cosine. So we start by turning that into a cosine, and remember that everything inside stays the same. However, we have to remember that we also need to make sure that we are multiplying this by the derivative of the inside. And I want to point out that here there's more than one term. So I'm going to use parentheses to represent this derivative and to make sure that it's written correctly. So the derivative of 4x to the fourth, we're going to get 16x cubed. The derivative of x squared is 2x. Again, these parentheses are really important because this cosine term multiplies the entire derivative. Okay, so that's the first one. You should have these two terms. You should have the cosine term and the derivative term. For the second one, we'll set up a substitution here. So I notice that I'm taking the cosine of the natural log. So the natural log is what's inside the cosine argument. So that's going to be my z. And then my y becomes cosine of z. So when I find dz dx, I'm taking the derivative of the natural log, which is 1 over x. And for dy dz, I'm taking the derivative of cosine, which is negative sine. Now I want to multiply these two things together. So I have 1 over x times negative sine z. So again, I don't want a z in my final answer. And then here, I can multiply this negative sine z into the numerator. So I'm going to write this as negative sine, and now I'm going to substitute in for z, natural log of x, over x. Okay, so again, I brought this term into the numerator, and I substituted back in for z. So I should get something that looks like this for my derivative here. So lastly here, we have this example. So we have a particular day that we're looking at the value of a stock, which we're calling V. It opened at $45 a share at 9 a.m. and closed at $45 a share at 5 p.m. It varied throughout the day. And what's here we have with time t in hours since 9 a.m. That's going to be important for us. And we can model this by 38 sine of pi over 4t plus 45. Find the rate at which the value of this stock is changing at 1 p.m. So whenever you see like find the rate, determine the rate, we're talking about the derivative. So we want to figure out the value of the derivative at 1 p.m. But before we can plug in anything for 1 p.m., we have to make sure we have the derivative to plug into. So there's two parts to this original function. There's the 38 sine of pi over 4t and the 45. The derivative of 45 is going to be 0 because that's a constant and it's all by itself. The first term, however, we have the 38, which is a constant multiple. And then we want to take the derivative of the sine term. And we notice that we're going to have to use a chain rule here because of this pi over 4. The derivative of sine is cosine of pi over 4t. So we turn the sine into a cosine, but then we have to multiply that by the derivative of the inside. So if you have pi over 4 times t, the derivative is just pi over 4, because that's a linear term, and we know the derivative of a linear term is just that slope, so just the pi over 4. So now we have our general first derivative. Now we need to figure out what it means to be 1 p.m. So time is in hours since 9 a.m. So we have to figure out how many hours is between 9 a.m. and 1 p.m. So 1 p.m. is 4 hours after we started measuring, right? So that means we're plugging in a t equals 4. It would be really easy to think that you should be plugging in a 1 for 1 p.m., but that's not how this measurement is set up, okay? So we plug in a 4 for t. And then we very, very carefully plug all of this into a calculator. And as a reminder, whenever you're dealing in sine and cosine, you need to make sure that your calculator is set to radians. And we get negative 29.85. So we can see that our stock is decreasing at this time since the derivative is negative, and it's losing $29.85 for every hour that goes by. So this is part of the cosine function that must be on the decrease, right? Because we're losing value on our stock here. So that's what that one looks like. And that's sort of an example of why we might need to take derivatives of sines and cosines. So that is all the different types of models that we have. So we have the power function, we have exponentials, we have the natural log, and we have sines and cosines. So the last piece to sort of bring it all together is what happens if you have more than one chain rule in a problem, okay? So there are times that you will have multiple chain rules, and it's not a lot of the time, but we have to be really, really organized and really, really careful about how we approach these. So these are not easy. These are definitely like on the harder end of the types of chain rules that you would have to do for sure. And so if it seems really overwhelming at first, that's okay. If we're really careful about being organized, we can figure out how to approach these. So we're going to do the first one together, and then I'll have you try the second one. So when we start with multiple chain rules, we want to start with the outermost function. Okay, so the first thing we're trying to do is determine what type of function is the outermost function. And so here, for example, everything is raised to this 10 power, right? And we said, okay, well, if the variables are in the base and it's raised to a numerical power like 10, then we have the power rule. So we're starting our derivative here with a power rule because this 10 power is the outermost function. And you can do this with a z substitution. I'm going to just talk through it using the sort of conceptual understanding, but either way, you will get the same solution here. So if I'm dealing with a power function first, right, this is a power function. The way we approach a power function is that the 10 will come down, everything inside will stay the same, and then that'll be to the 9th power. So I start by just writing down all these little pieces. Okay. So I have 10, everything stays the same to the 9th power. But remember, I now have to multiply this by the derivative of the inside. Okay, so the derivative of the inside means I now need to look at what is directly inside the parentheses. And when I do that, what I notice is that I have a natural log function there. So I'm going to have to do a natural log chain rule to fill in the derivative of the inside. So for the natural log chain rule, I remember that thinking about the derivative, I can do 1 over whatever's inside the argument. So that's x cubed minus e to the 2 to the x minus x cubed plus 1 plus 6. So I just wrote that in the denominator, but then I have to do the derivative of that, whatever was inside, in the numerator. So I say, okay, let me take a look at whatever was inside here and bring that into the numerator. So I'm hyper focusing in on these terms. So the derivative of x cubed, 3x squared. The derivative of 6 is 0. The derivative here, though, is going to give me yet another chain rule, right? Because now I have e to something, which is an exponential form. So when I take the derivative of an exponential form, I remember I get the same thing back. So e to the 2x minus x cubed plus 1, but I have to multiply that term by the derivative of the power of e. So the derivative of 2 to the x is 2 to the x ln 2 minus the derivative of x cubed is 3x squared, and the derivative of 1 is 0. So I've now done all the pieces, and my final derivative looks like this. Now, this derivative had every single chain rule in it. So this is like, expert level chain rolling. If you don't get it the first time, that's totally fine. The idea is to start working through the process of how to identify, like, what is the outermost form? Is it a power? Is it an exponential? Is it a natural log? And then working your way in, okay? So we're just gonna practice these to get good at them. It takes a while, it takes some practice. So I'm gonna have you try number 2. Hopefully you can see this. It's e raised to the power of x cubed minus 2 ln 5x to the 8th, all to the 16th power. Okay, so I want you to think about what is the outermost form. How do we then start to do the process of taking the derivative of the outermost form based on how you take that derivative? And as you're going through that, what other chain rules come up that we have to deal with along the way? Okay, so I'm going to give you about 3 minutes to try this one out, and then we'll go through it together. Again, if you don't figure the whole thing out, that's okay. See what pieces you can figure out. All work is valuable work. And then we'll talk about it in about 3 minutes. All right, take about 30 more seconds. All right. So again, I think one of the trickiest parts of starting these problems is figuring out the type that you need to start with. And so I'm looking here, and what I really notice is that the variables are all in the power of E. So there's nothing here that supersedes this to make it so that the variables are not in a power. So I'm going to start with the exponential form. And so our rule for exponentials when we're taking the derivative is that we start by getting the same thing back. So I'm just going to copy down what I started with. So e to the x cubed minus 2 ln 5x to the 8th to the 16th power. But then I have to multiply that by the derivative of the power, right? So now when I think about the derivative of the power, I'm thinking about this entire function, and I'm thinking about what type of function is the power. And I see that I have parentheses raised to the 16th power. So now I have to think about a power rule. So I think about the power rule and I think, okay, so the 16 will come down in front. Everything inside will stay the same. And I subtract 1 from the power, right? That's the outside part. But then I have to remember to multiply that by the derivative of the inside, right? So now I think about what that's going to look like. The derivative of x cubed is 3x squared minus, now I have 2 natural log of 5x to the 8th. So that is another chain rule in itself. So I'm going to do this up here in a side space. So here, the 2 is a constant multiple. So that's going to multiply the derivative. And the derivative of the natural log of 5x to the 8th. So I remember that whatever is in the argument, I can do 1 over that. But I have to remember to multiply that by the derivative of that term. So the derivative of 5x to the 8th is 40x to the 7th. Okay, so I think about how I might simplify this. 40 divided by 5 is going to give me 8, and 8 times 2 is 16. My constant's going to be in the numerator. And then I think about these x's. I have x to the 7th in the top and x to the 8th on the bottom. So all 7 of these x's will cancel with 7 of the x's here and leave me with 16 over x. Okay, and that was the last term as I was going through and simplifying. So my derivative is long, and there are a lot of pieces. And some of these things we just learned about today, like the natural log, right? So again, if this is not clicking for you right away, that is normal. It usually takes having to do 5 or 6 or 7 of these to really get used to the process of all the pieces. But the better you know the process for each individual type, the easier it makes doing the multiple chain rules. Okay, so that's the last one for today. Next week, we're going to do the product and quotient rule. But I, again, recommend that you start working on this homework early, and I would try to finish the homework before the quiz if possible, so you feel really good about the algebra. All right, I'll see you guys all on Tuesday.